Here's another example. We have w is a function of x, y, z, and t. So this is our function. And we have here a constraint that specifies the relationship between x, y, and t. So if they ask us to find dw, dy, and they have a little note here about x and z, this means that not only is y independent, because you're taking the derivative with respect to y, but also that x and z are independent. That means when you change y, x and z are fixed. If x and z are constant, then when you change y, then changing y will affect t, right? So t is a dependent variable. Let's see what happens in this case when we go to take dw, dy, allowing x and z to be independent and therefore constant when we take the derivative. Okay, so we take the derivative with respect to y. Well, x is independent of y, so that derivative is 0. The derivative of y with respect to y is 1. The derivative of z with respect to y, since z is one of the independent variables, changing y has no effect on z, so that derivative is 0. But then we have the derivative of sine t. Because of this constraint, you can see if you change y, t is going to have to change, right? So, whereas x won't because x is independent of y, so change in y can't affect x. So we take the derivative of sine t, and we get cosine t times the derivative of t with respect to y, because we're taking the derivative with respect to y. Now we can look at our constraint to figure out what dt dy is. If we just take the derivative of both sides of this equation with respect to y, we'll get it. So the derivative of x with respect to y, since x is independent in this case, that derivative is 0. And the derivative of y with respect to y is 1. And the derivative of t with respect to y would be dt dy. So we see in this case that dt dy is 1, so the answer is 1 plus cosine t. That's when we take the derivative with respect to y, assuming that the constraint has that x and z are independent and that the constraint determines t. So in this second part, though, they're asking us to find how does w change when you change y, but this time they're saying that z and t are independent. So if z and t are independent and y is also obviously independent, then x must be dependent on y and t. So this time, since x is not here and it's not in the list, x must be the one that's dependent. So we go to take the derivative. Well, since x depends on y, z, and t, then we get 2x times the partial of x with respect to y. We take the derivative with respect to y of y, and we get 1. Z is independent of y, so the derivative of z with respect to y is 0. And t is independent of y, so the derivative of sine t with respect to y, that's constant as far as y is concerned, because t is an independent variable. Just because you change y doesn't mean t has to change, right? T is actually held constant when we take that derivative. Alright, so now we need to find dx dy. We go back to our constraint, which said that x plus y is t. So we take the derivative to find dx dy. Let's take the derivative of both sides with respect to y. So we get dx dy, and we get dy dy, which is 1, and t is independent of y. So if we take the derivative of t with respect to y, changing y doesn't affect t, so there's no change in t, so that's constant. So that tells us that dx dy is equal to -1, which we can then plug in here. So we get negative 2x, because dx dy is -1, plus 1. So we got two different answers, right? But notice we had two different notations, so they really are different answers. How does w change when you change y, assuming x and z are independent, versus how does w change when you change y, assuming that z and t are independent?